So today we're going to review last week's content, that being both the applications of polynomials and the applications of exponentials. Now, I will say, as far as Saxon exams are concerned, one is significantly more likely than the other, and that's going to be the applications of polynomials. So I would say, unless you specifically want to make sure you've got your applications of exponentials down pat, I would recommend that the bulk of the lesson be focused on polynomials. Do you have any preferences? Let me know if you do. Okay, so let's recap. Applications of polynomials. One of the applications is simply just a matter of being able to create your own type of polynomial. In this case, I've given the example of cubics, but the same rules apply no matter what to any type of polynomial. You'll have a sequence of different possibilities for how you could structure your polynomial, whether it's fully factorized, fully expanded in the polynomial form, or in some sort of completed square or completed cube, if that's even a thing. The turning point or inflection point form. Those will all exist for all types of polynomials. So how do we know what to do and when? A lot of the time you'll just be given either a graph or literally just this information in words. Like, for instance, if it was worded, you would be told that the graph has an inflection point at 3, -1, and it has another point 4, 1. Find the rule of the cubic. That would be some sort of wording for that kind of question. Because we have so many different forms of how we can write cubics, we need to use the information that we're given to figure out where we should begin. And because one of the key pieces of information is the inflection point, we're going to use the inflection point form to help us out. So if it's at 3, -1, that means we can chuck a -3 and a -1 in the B and the C spots. No matter what, you'll always have this A that's left over, depending on what scenario you have, and you'll always be solving that. Like, again, we're talking 95, 99% of the time, with the additional point. You'll simply take the coordinates from here, sub it into what you have left over, and that'll get the A on its own eventually. If your question is asking you to solve A, B, and C, you would give A equals 2, B equals -3, C equals -1 as your final answer. If it says find the rule of the cubic or find the equation of the curve, anything to do with the actual rule, the equation of it, then obviously you then give the answer as your actual rule itself. Any questions so far? Okay. If your key information is all x-axis intercepts, well, mostly x-axis intercepts, then you should use the factorized form of the cubic, simply because the null factor law will tell you where x-intercepts are. So if you know that you have x-intercepts at 1, 2, and 3, you now have x-1, x-2, and x-3. Once again, the leading coefficient there is left unsolved, but we have another point that's involved. So we sub in that point, solve for A, and, well, the same is true as before. Give it as per the actual requirement of the question. A, B, and C, if that's what's required, or the rule, if that's what's required. If one of those intercepts is a turning point, we make use of our understanding of cubics to not only have it as a factor, but as a repeated linear factor. You've got a square on that thing now, because any turning points on the x-axis when it comes to cubics, or any polynomial for that matter, is going to have, well, no, for cubics it'll be squared. For anything else, you might get other even powers, but we don't really have to worry about that. As far as Saxon exams are concerned, you won't ever go above cubic or quartic. But yeah, this one was -2, so the squared term is going to get the +2. This one was +1, so the linear term is going to get the -1. Once again, A is left over, sub in the remaining point. This one's a bit more hidden, but we do in fact have a y-intercept there that we could plug in to get that A. And lastly, if you have 4 random points, we looked at this one in last class, basically you would do a full simultaneous equation. So you would define this directly in your CAS, the whole expanded polynomial, ax cubed plus bx squared plus cx plus d, and in your simultaneous solve, you're going to put all the points in equation form. All right, so for instance, we have negative 2, 7 as one of the points. That's going to correspond to f of negative 2 equals 7, because that's where the x goes and that's where the y goes. This will never be tech-free. You just, yeah, that's way too much work. You've got to do a 4-way simultaneous, which you may have done that, like when you first were learning about simultaneous equations, and your teacher may or may not have been like, hey, here's a really nasty bullshit question. Go have fun with a lot of algebra. Basic is the basic idea is the number of unknowns that you have is the same number of equations you should have. That's not necessarily always the case, but yeah. Oh, hang on, I've got a question. Would we be able to do a practice question for this graphing of the polynomials? Yeah, we can do that. I'll just wrap up. In fact, I think we're pretty much already wrapped up on this bit for now. Do we want to practice this, or should we move on to the graphing right away?
Can you practice one of these?
Yeah, certainly. So let's give that a shot. I saw a few back here in the chapter review. I want to go for that one, or I think this one's probably a bit, no, that's fine. We'll have a look at question 3 here. So give that a read, and in the meantime, actually I don't even need my phone, I could just use the CAS, because we are going to be CASing this one out. Yeah, let's have a read of question 3. We are going to be trying to use the key information given to us to at least start with 3a, and then we'll move on to part B to actually do some analysis of it. I hope this CAS will fix itself out because it decided to reset apparently.
Is this from the 1-2 or 3-4 textbook?
This is from the 121. But this is very, like, all of these are basically the same across the two books. At least as far as like what's required for the questions. They might have a bit more of a different story around the things, but still just fundamentally, here's 4 points, find the cubic. Yeah, alright, my CAS is up. Any ideas on how we would start this one out?
Did we start by? I think it was just, I can't fully remember. It was like this simultaneous equations, something we did with that.
Yeah, for sure. So using some simultaneous equations is what we'll end up with. You'll notice that the simultaneous equations are a bit simple in this one here. Right, we're able to use f of x notation for the whole thing. How are we able to do that in the CAS?
I think you have to define the equation, like the form of the cubic first. So yeah, the ax squared plus.
That's the one. Awesome. That's what we'll do first. Bit of a tip when you're defining things, make sure to put multiplication signs between all of the variables. So for instance, I'm defining h of x. I don't just do ax cubed, I do a times x cubed, because your CAS believes that ax is its own variable. If you do a times x, it'll split them up. So b times x squared plus c times x plus d, and yeah. So as far as getting to the simultaneous equations on the TI, menu, algebra, solve system of equations, solve system of equations. 4 variables, a, b, c, d, and we get our setup there. If you guys need me to work with it on the Casio, happy to do that as well, should you wish. Just let me know if you need it. But we'll finish up this one at the very least first and then go back to that if we need to. How do we now start filling this out?
Yeah, I think this was the part I was a bit unsure about.
Bit unsure about? Sure. So I'll pull up the previous set. It's going to be a bit hard to get it all on the same page. I'm going to zoom out as... Okay. That gets all of it on the same page. Is that still readable on the screen shares?
Yep.
Okay. So there's some correlation between what's on this picture and what's in this graph, what's in the simultaneous. Before I just sort of tell you the correlation, I'll let you guys take a stab at trying to guess.
I mean, like you could sub in, like obviously because f of x is just the same as y, you could just sub in for the y and x for
That's
each
exactly it.
point. Oh, okay, sorry, I was just overthinking it.
No, that's fine. No worries. It's a good question to ask. And so yeah, we have our sequence of points here, so if you give me at least one of them, we can figure this out.
Got uh 0x correlating to 15.8y.
Yeah, that's it. So in other words, when we put it into this CAS, we'll say h of
15,
0.
oh, sorry.
Yeah, no, go ahead. Finish it.
Um, oh, okay, so we don't put it in as y or anything. We just put in h of 0 and then equal to 15.8.
Yeah, that's right. So basically, it sounds like you wanted to do the 15.8 first and then the h of 0. It's fine.
Yeah, yeah.
It doesn't matter. It's the same thing.
Okay, yeah. Oh, but you don't have to put in the whole equation since you've already defined it.
Exactly right. Yeah, that's how we're saving some time there. But yeah, like you can flip these orders. So now I'm going to do the y first and then the x. So h of 10, it'll still come out fine. I've just tended to default to this sort of stuff. 6, and then lastly, h of 20 is equal to 15. Okay. Yeah, I guess the fraction's the only thing that makes sense since we're not told any decimal places there. Yeah, that's our set. How do we actually answer the question, having done that?
Um, are these points like intercepts or I mean because we've got one which is h for 0, but
Yeah,
I'm not
so
sure.
that's a y-intercept for sure. The rest of the points are just whatever x and y's. You only ever get intercepts if one of them is 0. X equals 0 means a y-intercept, y equals 0 means an x-intercept. We don't have any other information about whether they're like turning points or anything like that. Kind of ambiguous, but not super relevant. What's question 3a actually asking you to do? As like when you give a final answer, what does it
We're
want?
finding the values of a, b, c, and d.
There we go. Absolutely. So rather than writing the entire rule out by subbing in these A, B, C, Ds, we just give those A, B, C, Ds. And that's it. So pretty much exactly as it's written on the CAS is what you give as your final answer. I was just looking to see if anyone would try to give the rule instead, because that's technically incorrect. Fair enough. Okay. And then yeah, part B is just a bit of a bit of follow on from that. So we now have the rule. What is the coordinate closest to the ground? What is furthest from the ground? This is where understanding a bit of the actual background is going to be a bit helpful. Let you guys have a read of that. I'll just start defining all the variables and filling out the rule because that'll be helpful. Any ideas how you might approach BI or even BII? All the same.
Wait, just to clarify, it's not including the coordinates they've already given us. It's from any coordinate on the graph.
Yeah, so the shape of the branch is being modeled by the cubic. And so, yeah, it's not just going to be out of the points given, it'll be out of the net cubic that we've just created. Yeah.
Okay, so I think I forgot how to do this, but I think it's to do with the minimum and maximum.
Yeah, it'll be the minimum and maximum, absolutely. So closest to the ground, furthest from the ground. The ground in this case is just y equals 0, the x-axis. So basically as tall up the y or as short up the y as you can be is what we're looking for here. That's right. How do we go about doing that on a CAS? There's only really maybe two ways to do it because we're not told we have a number of decimal places to work with. We have to get exact. So I'll rule out one of the answers for you, which is we can't really use the graphing tools. Like we can't just put this in a graph and then use that because it'll only ever give decimals, which could be subject to rounding errors. There are some functions on the CAS calculator page specifically that can do this for us. There's two ways you can do it. One of which is calculus, so that's a bit too far ahead from where we're at. Yeah, if you haven't got it yet, I'll just jump in. So it is still under the calculus menu, but it's these function minimum and function maximum functions. If you want the minimum, you do the minimum. If you want the maximum, you do the maximum. So the first one says we want it closest to the ground. Does that mean we want a minimum or a maximum?
Minimum.
Yep. So we'll go ahead and do exactly that. Fmin of h of x, comma x. Now, if I just hit enter on this, we get an infinity. Our branch is clearly not infinitely long, so we have to restrict the domain in some way, shape, or form. What would be a good idea as far as choosing a domain for this? We aren't necessarily explicitly told what to do here. It doesn't say set domain equal to this. What seems like a reasonable choice?
Just not including anything below 0, because obviously the ground would be at 0, are we assuming?
So the ground is at y equals 0. Domain is all your x values. So
Oh, okay, yeah. Go back to the question.
yeah, that'll be
Oh,
a good idea.
up to 20. Sorry, I didn't see the,
That's it.
yeah.
That's the one, yeah. 0 to 20.
But if you had to do a range, it would be everything above 0, right? Like
yeah,
obviously it's not relevant to the question, but just
yeah. As far as what expected range you would have, we don't really have any upper limit on how tall this thing is going to look. So yeah, anything above 0 should be what we would expect. If the branch is going below the dirt, I'd be surprised. But yeah, and what you find is if you set your domain correctly, you do get an actual specific point. Now, I don't think they meant for this to be the answer. If we just quickly control enter it, we do get roughly 5.6, which if you look back at the picture, if that's 20 meters, then 5.6 seems to be all right enough, looking at that dip there. The book does get a bit ambiguous as to whether or not you should round it or not. VCAR will always, and your SAC will always tell you whether you should do a rounded decimal or exact. Sorry, I should say, you only ever give a decimal if it asks for decimals. Otherwise, the default is exact, which even though it's a big nasty number, that's the one we've got. Now that's the x value for which there is a maximum. this is asked for the coordinates of the point, not actually like, yeah, what we've got so far is just an x value for that coordinate. How are we going to get the corresponding y?
Just subbing the x into the equation
That's it.
because we already know what a, b, c, and d are equal to.
Absolutely. So let me fix this. H of that. And yep, another nasty number. 13.8. If we look at the range of the values that we had in all of our points, 13.8 is in the ballpark of all of them, and definitely the lowest of them all. So we can do a quick little, yeah, validation there. Even our own little graph as well, if we wanted to. We can go over here and we can plot h of x and just sort of observe what's going on there. Zoom fit's probably going to fail. Yeah, I hate that it does this, making it look like a graph that isn't actually what we've got. Let's see if we can fix this domain 0 to 20. And I guess we'll set these okay. So 0 to, probably 0 to 20 again, actually. And there's our branch. So yeah, you could then, if you wanted to further validate, hey, go through the graphing tools, get the minimum, and then we'll see that those line up. 5.6 and 13.8. 5.6, yeah, 13.8. That's pretty much it. So getting the rule was just a matter of doing our simultaneous equation on the CAS, and then the interpretation of that was, well, they'll differ from question to question, but a lot of the times they're just talking about either finding a y value or an x value. I don't think we need to go through the working out for furthest from the ground. That would literally just be doing the exact same thing, but now we would do our f max. So function maximum, syntax is exactly the same. Comma x, I know it's going to say infinity as well because we didn't set a domain there, but yeah, it's just the same procedure. Any more questions like that we should do? There is one that's a bit different here, but it's still fundamentally the same idea. Cool, okay. I'll pull up some notes for the graphing side of things and we'll have a look at that. Polynomials, quartics and above. So all we're really doing from here is extending on what we learned in the cubics section, which was our linear terms are always x-axis intercepts. They would always cut at a spot like that. They'll go from bottom to top or top to bottom. They go straight through. And we also had turning points that were on the graph. Those were whenever we had squared linear terms. They had a power of 2. When you work with higher and higher order or degree polynomials, essentially actually any even power will also be a turning point on the x-axis as well. So if we look at this one, power of 4, that gives us the x equals 5, and sure enough we have a turning point at x equals 5 there. The last possibility was inflection points. So any odd power beyond 3, and including 3, that ends up being an inflection point. And we kind of already understand this from the inflection point form of the cubic. It's a bracket x plus c cubed, right? You have this thing to the power of 3. So for instance, this one was power of 5. Again, it's an odd number. It gives us x equals -1. And sure enough, we get that inflection point going on. It goes and does a little bit of a wobble before continuing. Those are the main things there. This is an excessive exploration into it, but fundamentally really doesn't differ from whether it's just a power of 4 graph or otherwise. As far as where to locate those, let's have a look. They don't really put those cubed terms in there often at all. It's more so like it'll have straight up power of 4 there, in which case you'll know this is a turning point form thing. And yeah, a lot of the time you're not actually going to reach that cube, so it's pretty much just a matter of being able to work with those squared linear type stuff. So let's take a bit of a stab at it. Starting with, where's a good one? And they also end up being Cas as well, so that's kind of whatever. Is there really no non-Cas one? God, okay, I guess Unit 1 and 2, even 3, 4 probably also uses Cas for those, quote, more complicated ones, even though it's not really that much more complicated. So I guess we'll go back a bit and find a cubic section instead. Yeah, starting from around 3A would be good here. So, have a read of that. I'll pull up some notes, well, the handwritten bit, and we can do it live. Our goal is to sketch this. How are we going to go about doing that? One of the first things we can do is start getting our intercepts down, because those are just null factor law, x equals 0, y equals 0 type stuff. So even if we don't know the nature of them, we can at least get the solutions of them. What are we going to get for x-intercepts in this one?
Sorry, what was the question again?
So we're trying to graph the function overall, and I'm just sort of breaking it down into separate steps. Just getting the x-intercepts, how would we go about doing that?
Oh, well, since y is equal to 0, you can just use a null factor. So you know that in this scenario, x could be 1.
Mhm.
And I'm just trying to think. Or it could be 2.
That's it. Yeah. So simply grabbing each of these terms, making them equal to 0 and solving, gets you the x equals 1 and the x equals 2, respectively. Nice. As for y-intercept, that's pretty chill. How do I go about doing that?
Sorry?
As for the y-intercept, how do we go about doing that?
Just setting the x equal, sorry, x equal to 0. So
Yep.
-1
Mhm.
and then 4.
Yeah. 2 squared becomes positive 4. So
So you get
-1.
-4.
Yeah, -4. That's it. Cool. Okay. So we've got all of our key features there. All we're left with figuring out is the nature of these ones, whether they're cuts, turning points, inflection points, that sort of thing, and also where to start. Do we start at the top left, or do we start from the bottom left? So let's start with the nature of them first. This linear here, is that going to be a cut, turning point, or inflection point? I'll pull up the rules on the screen share.
Um,
Yeah.
Hello. Oh, okay. My audio's working.
Oh,
Sorry.
I think it cut out.
Um,
Yeah.
what did you ask last? I didn't really catch you. My internet's not very good.
Oh, sure. Okay. So the last question I asked was about what the nature of these intercepts are, whether they are cuts, whether they're turning points or inflection points. And I was specifically asking about this linear here, the x minus one. Is that going to be
Okay.
a...
The X minus one will be a cut
Yeah, that's going to be a cut. How do you know that?
because it's a well, the power is one.
Yeah, correct. There's this implied power of 1 up here, makes it a cut. Absolutely. Similar idea over here. What's the x minus 2 term going to give us?
It's it's going to be a bounce.
Yeah, a bounce, turning point. Similar idea, right? It's going to sort of bounce off of when it hits there. Perfect. So then we're going to cut through here. We're going to bounce off this. All that's left to do is to figure out, does it come from top or bottom on the right-hand side? On the left-hand side, sorry. How do we know?
We can look at the number of. Sorry. We can look at the coefficient of x
Yep,
in each of the factors,
yep.
and if
So,
we can count them, and if they're odd, it's going to come from the top or
if
uh,
it's odd, they're going to come from the top. So, just to be
oh wait, no,
clear, when you're counting, are you counting powers of x's or coefficients of x?
coefficients.
Coefficients. Okay, so you're saying this is a positive, positive, positive?
um
Is that what you mean?
yeah.
That's good. Yeah, because that's what you're looking for. Um, yeah, so positive, positive, positive makes it a positive or negative.
um it's positive.
Yeah, positive. That's right. And what do we know about, even if we just think about the basic cubic, what do we know about the shape of the positive cubic?
um it uh it comes in uh from the bottom and then goes out to, to the top.
Like this?
Yeah.
Yeah, that's exactly right. So in other words, bottom left, top right. And so having understood that, we also have a positive cubic here. So we're going to do the exact same thing. I'm going to come in, going to cut, like we said, and we're going to bounce, like we said. And that's our graph. We cut, we bounce, and we make sure we're doing our bottom left to top right because it's positive. If there was a negative out here, for instance, we would have the opposite direction, which wouldn't really work because now this negative 4 would flip over to here. So one little trick you can use for self-correcting as well, if you don't like the idea of imagining the basic cubic, is if you know where the y-intercept is, there's only really one way you can draw this, right? Because if you try to go from here and try to hit that y-intercept, you're creating another cut, and we don't have that. Like we didn't find that as a solution. So the only way we can actually draw this while maintaining the correct y-intercept is by going from the bottom, because the top, there's just no way we're going to hit that without crossing over. Cool. Okay, we'll try a similar one to that. It's going to be a bit masked though. I know it tends to throw people a little bit. It's going to be the part B, so 3b, where we have y equals x squared bracket x minus 4. This is basically the same graph, but it does look ever so slightly differently. How are we going to go about graphing this one? We can do it a similar way to before if you want as well, where you just find the x and y intercepts and then take it from there. Depending on how comfortable you are with these things, you can sort of just go straight into it. Like knowing this is x equals 2 and a turning point, knowing this was x equals 1 and a cut, and knowing it's positive, so bottom left, top right, you can sort of do that all in your head eventually. But if we want to do a step-by-step here while we're getting used to it, that's totally fine. So let's start with our x-intercepts. What are they, or how could we find them? I think you've come off mute, but nothing's come through. Might be an audio issue.
Okay, okay now it works. I don't know what's going on with my mic today. So the first x-intercept is 0,
Yep. That's good.
which is also the y-intercept, and the other x-intercept is 4.
Perfect. Yeah. That was just a null factor law, right? X squared equals 0, in which case you get x equals 0. X minus 4 equals 0, in which case you get x equals 4. Perfect. All right, that's x and y, actually, which is nice. All we're going to do now is figure out the nature of them. So have we got turning points? Have we got cuts, basically? Which one's which?
The squared factor is a bounce, which is
Yeah.
bounce origin, and there's a cut at 4.
There's a cut at 4, absolutely. So yeah, we've got our bounce, we've got our cut. All that's left to do is to figure out, are we starting from top or bottom left? This one could actually have a couple of ways of doing it because technically, you know, if you're just looking at, if you're just looking at the features that we have, we could reasonably still maintain by doing both ways. But there's better than our guess and check. We do know concretely which one it's going to be. How do we know? Well, it's something to do with the counting coefficients.
We can okay, so for this graph, it's it will arrive. It will come in from the bottom left and go out on, and it will like bounce off the origin and then cross 4.
Perfect.
And
yeah, that's exactly right. Bottom left because it was net positive. There's a positive there. There's 2 positives there. That's a net positive cubic. Yeah, if you had a negative here, it would flip, but otherwise, perfectly fine. Yeah, no notes. Reason why some people will get bothered by that one is because they'll imagine everything in brackets, and just having an x squared at the front usually throws people, but good you guys are able to spot that pretty quickly. If you have a look back at the textbook, there are ones that are in non-factorized forms. The only way you're ever doing this tech-free is if it is in a factorized form. So part D is fairly trivial. You just take a common factor of x squared out, and then it basically ends up looking like what we just did. Part E and F, those are a lot more complicated to factorize. Who remembers the ordeal, the procedure we have to follow for like our E and F factorization? Pretty unlikely it'll be SAC related because it is such a long procedure. I'm curious if anyone remembers it. because the techniques in there are definitely still valid for those who are doing a polynomials test or a test with polynomials on them eventually. Let's say it's about midway through the chapter. Oh, no, actually, it's actually pretty early on in the chapter. Okay, it's the factor theorem stuff. So if we go back to, geez, how far? Let's take a look. 6C. Yeah, doing the whole factor theorem stuff. So it's like, hey, factorize the following, and you'll see very similar setups to what we had before. And if we have a look just at like one of their examples, basically you would be, oh, not that one. And that one's a bit tough as well. Yeah, something like this. So you'd have your cubic, and you would start by listing out these factors, right? So it's going to be the plus, minus 1, 2, 3, and 6, respectively. And you're essentially subbing those into your function to eventually get 0. It was just a guess and check method. You would start from the easiest, go to the hardest, until you get 0. Via the factor theorem, that proves that a certain term is going to be the factor. You would then use that for your polynomial division, which is its own thing. And then the quotient and factor become your two factors, which you can maybe further factorize. We won't look at that today, but that's just a refresher on what you need to do in order to get those into a sketching form. You need them in a factorized form. Doing this tech-free otherwise is not really doable. So if you are going to go ahead and do the remainder of these questions, where are they? The remainder of these ones, you would have to go through the whole factor theorem, remainder theorem, guess and check stuff. It's worth doing it just to remember how to do it, but it's unlikely to show up unless they give you a lot of marks for it in the SAC. And everything else in here is just CAS, so there's not too much point having a look at that because you literally just take exactly what's written there and write it exactly in your CAS. And as long as you know how to use all the graphing tools to figure out your maximums and minimums or whatever else it needs, then you can just copy and paste directly down. Does anyone need to see a CAS run through of any of these? Or are we happy enough with how to use it? Thumbs up for a yes, go through. I'm so confused. I'll do a quick run through and someone shut me up if I'm misinterpreting this. Cool. So on the graph, go to your graphing tool. No one seemed to care about me doing the Casio stuff, so I'm supposing we're all got TI Inspire here. Yeah, you hit tab to open up your entry, and let's say we're doing 4a, for instance, right? It's the x minus 1 bracket x squared plus 1, so we're going to do exactly that. X minus 1 times bracket x squared plus 1. We get our graph, and what's it actually asking us to do? Draw a sign diagram, which is kind of irrelevant, never really required for anything beyond the book. Label the sketch with points of intersection, so axes intercept, do not do turning points. No, even easier, don't even need turning points, which this one doesn't have any, so it makes sense, I suppose. As for how to use it, so you go to your Analyze Graph section, so the 6 section here, and you've got a whole bunch of options here. 0, for instance, will help you with your intercepts. I think it does both. No, it just does the x. Okay. So it does your x intercepts. 0 does. Is there really no y intercept one? Really? That's a bit strange. I mean, I guess you don't need it, because y intercept is always just x equals 0. And
I mean, if you do need the y-intercept, you can always just do a graph like at like on the y-intercept and then just use the intersection.
Yeah, that's exactly. Well, you would have to know where that is, though. That's the thing. So unless you actually, so you wouldn't do like a y equals thing. You could do the x equals, which is actually worth discussing here. So in your graph entry edit, you can actually do vertical lines. It just takes a bit of effort. You go to this relations section here, and now you can do things like circles if you need to, but for what we're going to be using it for would be the x equals 0 line. And now we can do that. Now we don't necessarily. Wait, did I do the thing again? 26 intersection corners. All right, fine. But yeah, that's a bit of a hack around there. Because if we already knew the y value, then we would just give that, because that is the y-intercept. More likely, once you've got it defined, what you can do is you can hit this var variable button in here, and everything that you defined shows up in there, including the functions that you put in the graphing tool. So if you want to directly use the function from there, you absolutely can, just the same as if you had defined it on the CAS. So that will get you your y-intercept, and you can even do like a CAS solve around it, f of x equals 0, to get your x-intercept. So these things work bidirectionally. Anything defined in here can actually be used over here as well. Even the slider, if you do have like a slider in your thing, that c variable does actually get used back here as well. Just to explore a bit further, let's get another one, because there's one that does have turning points in there, and just for the hell of it, we'll explore a bit on how to do that. X squared plus 2 times bracket x minus 4. This one we're going to have to zoom out a little bit. By the way, the auto fit that I'm doing there, menu 4 and A, this zoom fit. Sometimes it's alright, other times it gives you crap like this, because it's trying to put it all in the same thing. Usually it gives you a decent X, but the Y is sort of lacking. So if we do, I don't know, let's just say negative 50 to 50. We can now, okay, that was just a shot in the dark, but we can now see those max and mins. In your Analyze Graph tools, you have min and max. So, yeah, just drag and drop. Click one side, click the other side. Doesn't matter where you start. And as long as you are allowed to use decimals, this will be appropriate. Otherwise, of course, you would do the fmin, fmax stuff that we were doing before. Don't drag it too far, otherwise it will find like these points over here. As you can see, if I drag it far enough, it's grabbing those. Keep it within the boundary. And yeah, same as before. Decimals you're only allowed for if you're told to use decimals. That's about it for the graphing stuff there. I don't think there's much more else to talk about. Anything more to discuss for graphing? If not, let me know. Because the last thing to have a look at will be the max and min applications. So for the max and min applications, you're following this 4-step procedure always. So whether it's volume, whether it's area, whether it's, I don't know, voltage, it doesn't really matter what the question is talking about. Like if we go through a few examples here, we've got things like boxes for volumes, we've got surface areas, we got, even more shapes. Okay, that one's just entirely shapes. There was some weirder stuff in here though. We had the tree branches, we had RPMs. So they can be a bit more creative with it, but they often don't. Step 1, no matter what it is to get an equation which only has one variable in it. Technically 2. You want the y and the x, but fundamentally you're going to start with the generic formula for that thing. In this case, we have a volume for a box, and the volume of a box is always length by width by height. So you get your picture. If you haven't already got a picture, you would draw it based on the information provided. And from that, you'll be able to determine what length, width, and height are purely in terms of one variable. which in the case of boxes is often going to be this cutout of x on either side. So your new width is going to be 10 minus 2x because you're cutting out 2 x's, both sides. Same thing with the 20 over here, which is why these both now have a 2x attached to them. The height is just going to be given by x because when you cut these things out and fold them inwards, this cutout side here is now your new height because you've flipped it upwards. So length, width, height, you've now got everything purely in terms of x. If the question is asking you to write the rule as a key deliverable, make sure it's either fully factorized or fully expanded. This is not fully factorized because there's still factors of 2 that you can take out of both of these terms. 2 from here, 2 from here makes a net total of 4. From there, this is just a cubic, so you don't even really need a CAS for this. You can just sort of draw this out, right? There's a cut at 0, there's a cut at 10, there's a cut at 5, 0, 10, 5. It's got a negative x here, and a positive. Negative, negative makes positive, and then positive keeps it positive, so we're starting bottom left and ending top right. From here, just turn your brain off and only look at this first bit. The reason why is because you cannot have negative volume. So pretty much always going to be the case that the bottom bit and anything right of here is no longer valid. You'll always have this sort of hump in these polynomial applications. That's where you'll focus all your attention. So if it asks you, what's the effective domain? There it is, 0 to 5. So you can cut it off if you want. You'll be doing that anyway when you do your Fmax. So whether you do it in the graphing tool or otherwise is fine. By the way, if you're doing that little cheat hack thing that I was talking about, where you define it in the graphing tool first and then use it in the calculator tool, if you put a domain in that calculator, in the graphing tool, you don't then have to do it again on the Fmax and Fmin because it looks at the function definition already in the graphing tool. So for instance, if I go through and limit this one, actually, do I have another one? Not really. Maybe I'll use the 1.4 actually. If I go ahead and limit this from 0 to, what's this going to be, 10 maybe? Oops. And then I go try to do Fmax on the F3. Let's try Fmin actually, because that's already cut off properly. And for function minimum, that was F3. Oops, I missed it. 3 of x. It's already taken into account that domain that we put on it in the graphing tool because it's part of the function definition itself. It's the same as if you were to, in the function definition on the calculator, also put a domain in there. If you define your domain here, you also then don't have to do it in the Fmax Fmin. I'd still recommend against it though. Putting a domain in here or on the graph should ideally be used sparingly. And the reason why is because it kind of makes things weird when you're using these solves and what's the other one that usually comes up a bit weird? I think composite functions can kind of break. Piecewise functions can kind of break. When you're putting these domains in there, for whatever reason, it just sort of gets a bit weird. It's not necessarily breaking, it just becomes kind of hard to analyze what it's actually done. So where possible, just sort of define domains as required. It's the little warning there. But anyway, cool. So that was a bit of a tangent. Only because I guess the continuation for this is sort of whatever. You've got your graph, you want to find the maximum, it's right there. You either use Fmax if you need exact, or you would use the graphing tool if you can do some sort of decimal places. We'll ignore all the what's this? Yeah, okay, this is diff. Yeah, we're not going to do diff. Cool. All right, we're about to run out of time on that one, so we don't really have too much time for a full-length go through together. So I might just blitz one anyway, but before that, is there any part of this that I should slow down for and explain in more detail?
I think it's all good.
It's all good? Okay. So we've got the creating of the equation, we've got drawing a sketch of it roughly, and then Fmax or Fmin, but pretty much always Fmax. Cool. All right, I'll try blitz through one. So we'll use this extended response here from the chapter review because it's a little bit different, but also kind of the same. All right, we've got a volume of a cylinder equation going on here. We're told what the generic formula is, and we're also told our supporting piece of information. We usually, like in the example we just looked at, we had a picture to work off of to get some supporting information. In this case, we're literally just told, here's equation 1, here's equation 2, do your rearranging. So we have V equals pi r squared height, and we have h plus r is equal to 6. We're trying to get r on its own. In fact, that's probably quick enough. Does anyone know what you do now to get r on its, to get only r's in this V? Got these two equations. This one's got a h in it. We're going to try and get rid of that h in terms of r. Any ideas? All good. H equals 6 minus r from the second equation, and because this is h, we can put it in there. V equals pi r squared 6 minus r. That's our equation, that's our thing sorted. Now this is just going to be some sort of cubic. It's got a turning point at, remember the r's are going to be our x's in this case. It's a net negative this time actually. It's negative and then positive, positive. So that's net negative. It's going to now turn at the origin and it's going to cut at 6. Sure enough, we have this hump sort of thing that we're going to focus on. Effective domain 0 to 6. Usually this is rounded bracket actually. They usually assume volume should not be 0, but the book doesn't clarify. Every exam usually will say the volume needs to be greater than 0. So that's A and B sorted. State the values that R can have. Those are the values that R can have. V of 3 is just V of 3, that's whatever. It's more so the part E in there, which is you'll essentially just do F max V of X, comma X. Well, I guess you could do R, but just use X's, it's easier. And you would then put your domain of 0 less than equal to x less than equal to 6. That'll give you some x equals whatever. You shove that back into v of x. And that gets you your final answer. Maximum possible volume. Cool. That was a quick-ish run through there. The bulk of the effort's going to be on getting the equation. Everything else is identical following that. Any further clarifications? If not, I'll leave you to enjoy the rest of your day.
Thanks, Chris.
Take care. Thanks.